Okay, welcome to an advanced math problem on trickling filter math. This requires a mastery of understanding hydraulic loading rate, which is measured in gallons per day per square foot. There's going to be I'm going to go over a couple things as we read this math problem out. There's a little bit of a lesson intertwined in this, okay? So we're going to get to the math. The math's actually not that hard. It's understanding how to get to the math that I think trips people up, okay? So let's read this math problem out. I'm going to give you a little lesson on trickling filter theory, and then we're going to work the math out. So a trickling filter is 80 foot in diameter with a maximum hydraulic loading rate of 860 gallons per day per square foot. The system processes an ADWF of 1,000 gallons per minute and PDWF of 2.5 times average flow. Stop there for a second. You should know what those two are because they might present it like this. They might also write it out, but ADWF is average dry weather flow, which is what you're normally getting. Like on a standard, day, we're getting 1,000 gallons a minute coming into the plant. Now, they might write this in MGD and you have to convert it because what we're going to ask for in the end is what is our recirculation pump being set at in gallons per minute. So just bear with me here. This might be an MGD. And peak dry weather flow, PDWF of 2.5 times average flow. PDWF is peak dry weather flow, meaning the most that you will anticipate you could spike to in terms of flow, your peak demand times that don't involve rain events, okay? So peak dry weather flow is exactly what it sounds like, and average dry weather flow is exactly what it sounds like, okay? This is typical, this is extreme. During peak conditions, the total flow must not exceed the max hydraulic loading rate of the trickling filter, which is 860 gallons per day per square foot. What GPM should the Recirc pump be set at to avoid hydraulic overload during peak flow? And follow up, what is the recirculation ratio of the ADWF? All right, so what they're getting at here is you can never really anticipate truly when and how long peak dry weather flow is going to happen. I have a pretty good idea because I've been working in my plant for a little while. I have a decent idea, but sometimes I get surprised and it sneaks up on me. I have a fairly sophisticated plant, but not one sophisticated enough where I've got SCADA ramping my recirculation pump up and down based off of flow rates onto the trickling filter. That these tests are not built around you having bells and whistles that do fancy things like that. They are anticipating that you work in a more rudimentary plant and you've got a static recirculation rate. Now certainly you'll make adjustments throughout the day, but you might get caught off guard or you might be working on something else and boom, here comes the slug, here comes a ton of flow and you're not anticipating it. You need to make sure your recirculation flow is not too high because you don't want to exceed maximum hydraulic loading rate, okay? So that's what this math problem is asking for. That's the little lesson. And if you were to exceed maximum hydraulic loading rate, you could start having sloughings off, extreme sloughing events off of your filter that's caused really bad downstream water quality in terms of your effluent. It could damage, and in essence, it's similar to washing out your biology on a activated sludge plant is hydraulically overloading your trickling filter. So just bear that in mind. And if you want more information on that, at the very end of this video, another video will pop up. It's on my trickling filter video I put out a couple weeks ago. I kind of demonstrate that. I go into a little bit more detail on hydraulically overloading a filter. So let's now figure out what is it that we need. We need a GPM, all right? So if I've got gallons per day per square foot, and I've got GPM given to me, and they're asking for GPM, what I actually need to do here is I need to change my hydraulic loading rate to gallons per minute per square foot, and then find out how many square feet I have, and then convert that to gallons per minute allowed over the trickling filter. And let me demonstrate this. So I've got an 80-foot diameter trickling filter. Okay, so 0.785 diameter squared, work that out on your calculator. 80 times 80 times 0.785 is 5,024 square feet. Now I've got 860 gallons per day per square foot, but remember, I'm being asked for gallons per minute. I got to figure out how much gallons per minute this trickling filter can take. So I'm going to take 860 and divide gallons per day per square foot and divide by 1,440 minutes in a day. I didn't write the units out for space, and also my marker's kind of getting dry on me again, so I got to get another one. I apologize. But what that gives me is 0.6 gallons per minute, and I didn't write it here. I should have per square foot. Per square foot, okay? 0.6 GPM per square foot times 5,024 square feet gives me 3,014 GPM. And I apologize, guys, I didn't put per square foot. So I'm correcting that verbally now. 0.6 GPM per square foot times 5,024 square feet, which is my trickling filter surface area, is 3,014 gallons per minute. That's how much peak dry weather flow, that's how much hydraulic loading the trickling filter is able to take. Now, average dry weather flow, we're going to now figure out what peak dry weather flow is. That is 1,000 gallons per minute is my average dry weather flow times 2.5 because that's peak dry weather flow. It's 2,500 gallons per minute is how much flow will be coming through the plant in peak times, okay? So I need to calibrate my recirculation pump to a point that it will not exceed 3,014 gallons per minute when added to the 2,500 gallons per minute, okay? If you have any questions about where we are so far, please put it in the comments below. I'm happy to dive a little bit deeper into this, but I think I'm trying to explain it the best I can. Also, before we come to the solution of the problem, if you're getting anything out of this, you're learning anything, please like, subscribe, and pass to your friends, and let's help folks get certified. The recirculation gallons per minute. All right, so what I've got here is I've got my 3,014 gallons per minute that my trickling filter can handle. Subtract the 2,500 gallons per minute from peak dry weather flow, and that means I will set my flow rate on my recirculation pump to 514 gallons per minute. Therefore, ensuring that my trickling filter will never be hydraulically overloaded because my peak dry weather flow is 2,500 gallons per minute. My recirculation pump is 514 gallons per minute, and that means that I will not, it's impossible for me to exceed the 3,014 gallons per minute outside some, cataclysmic event. They may ask for this answer in MGD. It's just, again, like I said, I've said this before, I can't anticipate every conversion on advanced math problems. They just change it up. So you just need to be able to, fluent enough in unit conversions that you're able to figure out what they're asking for and work through it. Now, they might follow up and say, okay, what is the recirculation ratio of the ADWF? What's your average dry weather flow recirculation ratio? And that would be, you would just take 514 gallons per minute, divide by 1,000, which is your average dry weather flow, and that gives you the answer, if you plug that in your calculator, of 0.5. And so that recirc ratio, you are at 0.5 to 1, which is an acceptable recirculation ratio. If you look at my trickling filter whiteboard, you'll see that recirc ratios can vary 0.5 to 1 all the way up to 5 to 1. It depends on what you're engineered for and what's going on, okay? 5 to 1 is really incredible, but mine's a 3 to 1, in case you were wondering. So anyway, yeah, that is an advanced trickling filter math problem, an iteration of an advanced trickling filter math problem. Be ready for different conversions, like I said. And I think this might also help clarify a little bit of that hydraulic loading stuff. Remember, you add recirculation ratio in your hydraulic loading. You do not add recirculation ratio on organic loading. I'm always going to take the opportunity to say that when we are doing trickling filter math. Even if we're not doing an organic loading math problem, I'm always going to say it. Anyway, like I said, if you got anything out of this, please like, subscribe. Any questions, please put in the comments below. If you saw a math problem similar to this, but posed a little differently, please put in the comments so people know what to expect. And we'll catch you in the next one. Have a great day, everybody.